Thank you very much for the introduction. Thank you also to Mestre Research for putting together what's blossoming into a really interesting and diverse webinar series, and thank you all for registering and taking the time to tune in this morning. So I'm going to talk a little bit about using the NMR-ready 60 megahertz benchtop NMR for quantifying the stereoselectivity of the Wittig reaction. So for those of you that aren't very familiar with Nanalysis, we were established in Calgary, Canada in 2009 with the mission to provide compact, affordable NMR into non-traditional applications. So whether that be at line in an academic teaching lab or directly into a glove box or a fume hood or even into an online reaction monitoring type situation. We have two models, our E, which runs high-frequency nuclei, proton and fluorine, as well as a Pro, which has multi-nuclear capability. They both have the same platform. Again, the mission was to make a compact NMR, so that was easy to cite. So in our minds, that meant it was an all-in-one enclosure that includes the magnet, the electronics, as well as a fully functioning Linux-based computer that can be controlled either as a touchscreen or remotely, either through a VNC or by a mouse and a keyboard. The whole thing weighs 55 pounds, so pretty much anybody can pick it up and move it around, and it was designed with the footprint to fit into the large port of a glove box. So you can have an idea of how large the instrument is if you've not had the opportunity to see it. The magnet itself is made from a hybrid hallback of neodymium iron boron magnets. This is important that it's a hallback because it means there's very little stray field associated with the instrument, and there's much less magnetic interference with instruments that might be around it on the benchtop. Again, because it's a permanent magnet, no cryogens are necessary, plugs into the wall, uses standard wall power, and is pretty easy to put into any environment. We use standard 5mm NMR tubes, as you can see from this portal, but it's also compatible with non-traditional flow cells as well. And the data is very easy to remove through a number of methods, and they're standard JCamp DX files that are compatible with most third-party processing software, and I will discuss mostly their compatibility with MNOVA for the remainder of this talk. We do have our own proprietary onboard software that makes it easy to initiate an experiment, to change your basic acquisition parameters, to do your basic onboard processing, whether that be phasing, baseline correction, apodization, integration, peak picking, all the basic things that you need to extract the information that you're looking for from your basic 1D spectrum. But of course, we also facilitate 2D experiments. So here's a cozy being run, or you can watch in real time relaxations, which is the T1 data shown here. The 60E, as I said, is a high-frequency model, so it runs 1D proton or fluorine, your relaxation variables, as well as your homonuclear 2D, cozy, and JRES type spectra. The Pro has multi-nuclear capabilities. This can be tuned to a variety of different nuclei depending on your application and what you're interested in, but most commonly we get asked for either phosphorus, carbon, and then deconvolution methods such as the depth 135 shown here, but as well HSQC and other 2D type deconvolution methods. So for those of you that are familiar with a benchtop, this is a little bit of a review, but I just sort of want to classify basic, the basic types of instruments. So what we're probably all most familiar with is the superconducting high field instruments that over time have moved to increasingly higher field. So this is important because it helps scientists understand and assign structure as well as absolute configuration to increasingly complex molecules, whether that be how proteins are folded or maybe long peptide chains, but we can understand things of greater molecular weight to a much higher standpoint. On the other end of that spectrum, what we call is low resolution. So these are magnetic fields that can range in their field strength, but are typically under 60 megahertz, and they're used for very specific applications, whether that be solid fat content, determination of moisture content. And then in the middle we have what we call our benchtop NMR. So we call these low field because they're less than 200 megahertz, but we call them high resolution because we have sufficient line shape that you can make out most of your spin-spin couplings, and you can do basic structure elucidations for small molecules. So these benchtop NMR will never be a competition for the high field, but there are a lot of applications where you can see the benchtop NMR being quite useful. So of course the utility of NMR as an analytical tool is essentially twofold. It gives you structural information as well as it's quantitative. So it can either be used specifically determine what isomers look like or what your connectivity and actual structure in your molecule is, or it can be able to determine how much you have relative to each other. So Benchtop's well suited to do both. So for the course of this talk, I'm going to talk about structure elucidation, QA, QC, and sort of reaction monitoring of the Wittig reaction. So just a little review. Of course, we all know that an aldehyde or a ketone, that carbonyl group, is an excellent source of reactivity. The electronegativity gives a delta positive on the carbon, a delta negative on the oxygen, which of course can give you a Lewis structure of a carbocation. The carbon is then prone to nucleophilic attack. The oxygen is prone to electrophilic attack, particularly through protonation, and this can give you sort of a wealth of reactivity. So you can think of either an oxidation reaction or reduction. You can form some carbon-carbon bonds through a variety of reagents, including the Grignard reagent, some hydrocyans, some amines, and what I'm going to highlight for this talk is the Wittig reaction. So the Wittig reaction won half of the Nobel Prize in 1979 because it's a high-yielding, versatile, and highly stereoselective reaction to form carbon-carbon double bonds. So not much that can be said of most other carbon-carbon double bond forming reactions like basic eliminations that give you a wide range of structural isomers. So basically you take a carbonyl, you react it with a phosphorane, you transfer the phosphorane's alkyl groups and make triphenylphosphine oxide. So initially the Wittig reagent was made by triphenylphosphine in a basic SN2 reaction with a primary or secondary alkyl halide to form a phosphonium salt. One of the CHs then on the alkyl chain is rendered acidic, and so depending on how acidic it is, you can react it with an appropriate base and generate either a phosphorane, or of course you can push the electrons and draw that as a phosphorus halide. So what's important about this is that this is a source of a carbanion, and you can effectively envisage it reacting very well with a positive charge on the carbonyl. So there was a lot of debate initially about how this reaction mechanism happened, but given the high stereoselectivity of the reaction, it most likely went through a concerted type mechanism, something like this, where you make an oxyphosphatane, this very unstable four-membered ring that rapidly decollapses to form a very strong carbon-carbon double bond, as well as your triphenylphosphine oxide. So this is used in a number of areas, including the formation of pesticides, nutritional supplements such as this acetyl vitamin A, for hormone treatments, for making synthetic hormone-like substances, optical whiteners, textiles and dyes, and then for what talk I'm going to focus mostly on flavors and aromas, specifically that of ethyl cinnamate shown here at the bottom. So there is a number of possible synthetic routes you can use to make ethyl cinnamate. For the purpose of this talk, I chose this modified procedure from the Journal of Chemical Education. It uses a stabilized Wittig reagent, so you don't have to make it in situ prior, which eliminates the need for strong bases, and it gives predominantly trans stereochemistry. I'm using it without solvent. I'm using benzaldehyde and stirring my Wittig reagent in a slurry, and then I'm removing the triphenylphosphine oxide to isolate my product. So this is an interesting molecule. If we use benzaldehyde as our starting material to make ethyl cinnamate, this is the main compound that's used in most flavors when you have anything that smells balsamic-y, spicy, or cinnamon. So this can be used for cinnamon candles, for artificial cinnamon type flavors. So of course you can use the Proton NMR to do basic reaction monitoring. I've shown here just a stack plot of my starting materials, my benzaldehyde, my Wittig reagent, and then the ethyl cinnamate that I've isolated. And of course you can also use phosphorus NMR to monitor this as well. So I have my starting material, which is consumed almost completely throughout the course of the reaction, and I get a new peak that corresponds to triphenylphosphine oxide. If we look a little bit more closely at these spectra, aldehyde, of course, is a nice NMR handle, so it integrates nicely to 1. We do have some second-order effects. We don't have complete resolution here in our aromatic ring, but you can make out the ortho and the meta-para protons, and we can look at our Wittig reagent as well. So we've got our triphenylphosphine, you have your alkyl chain, as well as your CH molecule. So if we look then a little bit more closely at our product, it's pretty easy to assign the ethyl group here on the side. I've got a triplet and a quartet, pretty typical of this ester ethyl group. If I look a little bit more closely, it's pretty easy to make out the aromatic group here, pretty indicative in the 7 to 8 ppm range. And then I expect to see 2 doublets here for my olefin peaks. So I've got a doublet here at about 6.3, which makes good sense, but I do seem to have lost one of the signals. So if I want to be able to deconvolute that, I can look at maybe some 2D spectra. So this is the COSY of the ethyl cinnamate. COSY, of course, shows you on the off axis, the off diagonal peaks, sorry, which spin couplings are correlated. So I, of course, see my ethyl group, my methyl, and my CH2 correlated, and here we can pull out that our other CH peak is actually overlapping here with our aromatic peaks. It's not well resolved. You can pull this out further. You can run a JRES. This is J-resolve spectroscopy. It's a nice experiment that helps you pull out the coupling constants. It separates the chemical shifts from the scalar coupling. So I've shown the spectrum up here, but up at the top we have our chemical shifts, and in the body we have our coupling constants. So we can make out nice 2 doublets for the CHs that are bonded, a quartet as well as a triplet for the ethyl group. So if you want to, the nice thing about NMR is it sort of shows you the manifestation of the chemical properties. So why are the CHs separated by such a large distance? If we draw the resonance structure here, you can of course push the electrons out. So the beta CH, the one closest to the carbonyl group, has a lot of electron density on it, moving it to an upfield position, whereas the alpha CH, the one closest to the aromatic ring, can have a positive charge on it, thus moving it a little bit further downfield relative to its partner. So the next factor that I would like to look at then is what is the stereoselectivity of this? Can we quantify it, and can we use the NMR spectrum to separate what is a trans and what is a cis isomer? So, of course, if we review back, there's a typical vicinal trans coupling between is typically between 12 and 24 hertz, whereas if you have a cis-related coupling, it's usually between 6 and 12 hertz. So if we look a little bit more closely, our major isomer has a coupling constant of about 16.2, which is well where we would expect for a basic trans coupling, and the minor isomer has one of about 12.6. So a little bit ambiguous, but it does suggest that the minor isomer is in fact the cis. And of course, if we look at the JRES and blow up the resolution, the intensity of the cross peaks a little bit more, we can of course pull out that cis coupling as well. So because this is a little ambiguous, I'd like to sort of pursue this a little bit further to see if we can more definitively decide which is the cis and which is the trans isomer. So the first way that I'm going to do that is use the basic NMR prediction plug-in tool like that available in MNOVA. So you can start by drawing the trans molecule using these buttons here on the side, and then I'm going to go to predict. So start by prediction options. I can predict the spectral width. I would like predicted the number of points, the frequency of the magnet that I'm acquiring my data on, the starting line shape, the solvent that it's in, and then when I predict it, I get a spectrum that looks pretty similar to what I observed. So this is a pretty nice tool to help you understand the differences between high field and low field, and also to help you rationalize what you're observing experimentally. So if I look then at the trans, the CH that's well resolved from the aromatic group, I can determine what the chemical shifts is, as well as get a predicted trans vicinal coupling of about 16 hertz, which is in pretty good agreement with what I observed experimentally. If I draw the cis and predict it, you'll notice that you can make out both the alpha and the beta CH, and it has a predicted trans coupling of about 11, or sorry, a predicted cis coupling of about 11 hertz. So if I overlay these two, this is exactly what I observe experimentally. What I think is my trans is located right in between both of what I've expected for my cis-based couplings. The next way I can look at this is do some basic Gaussian calculations. So these were done by Len Mueller at UC Riverside, where he was able to predict what the relative energies of these oxaphosphatane rings are. So you can predict if you put the benzyl substituent either in an axial position, which is what we call a 1-2 interaction, because it's predominated by the fact that the benzene ring is then approaching the ethyl group, which you can probably see from this Gaussian projection here. Or there's a 1-3 coupling, where the benzaldehyde base group is in the equatorial position, and the main source of interaction is interaction between this phenyl ring as well as one of the ones on the phosphorus group, as you can see here. So the 1-3 interaction is of slightly lower energy. The difference between the two is about 6 kilojoules per mole. So if I assume that this is a kinetic control, you can predict a relative cis to trans ratio of about 93% trans and about 6.8% cis. So again, going back to my experimental data, I've got my trans in the middle here and my cis surrounding it. So comparing the 60 and the 400 data, experimentally we observe about 96% of the trans and about 4% of the cis. Good agreement between the fields, even though the 400 does have much higher peak separation. So this is the next point that I want to talk about is this is all good, as I've shown you, for an expert to be able to look at the data, extract the information that they want. But in order to move these instruments into non-traditional fields for QA, QC, in maybe a pharmaceutical or a flavor company where it has not been used previously, we need to find a way to be able to automate the data process to make it a little bit easier for people to use. So one of the ways that we've been experimenting with is the MNOVA Simple Mixture Analysis plugin. I've shown here. So you start by just opening the spectrum that's of interest. Advanced, pick SMA. So you can have a scientist or someone who's familiar with the data or how to solve an NMR spectra, set up a basic experiment where all I do is I say the trans isomer and I specify the chemical shifts which I expect it to come to, the multiplicity I expect it to have, the J coupling I expect it to have, and how many nuclei correspond to that signal. And then you can just do a ratio of the two automatically. So all that a chemical technician would have to do is run a quick sample and hit analyze, and they'll immediately get a value for the trans and the cis percent. So again, I've got 95.56 in perfect agreement of when I did it manually. And of course, you can easily create a report that displays nicely so you can see the relative couplings without having to do any of the data analysis personally. Just want to digress a little bit here. One of the nice things that we're trying to do with Benchtop NMR as we move to non-traditional markets is explore the difference between proteo and deuterated solvents. So academic teaching, potentially the cost of deuterated solvents can be a little bit concerning, or even on a manufacturing or QA QC line, the idea of using deuterated solvents is an added sample preparation step that's not necessarily conducive to using NMR. So we do a lot of studies to see how accurately we can compare results taken in proto and deuterated. So I've run it here in protonated chloroform just to make it the same, but of course you could pick a better protonated solvent, either dichloromethane or maybe an acetone that would not overlap with your chemical regions of interest at all, and you see that I get numbers that are almost identical when I look at my cis to trans ratio. I still have 96% trans, 4% cis. So just for the remainder of the talk, I just want to give two more examples here. So this is going to be, I'm going to look at starting with a para-nitro-substituted group and a para-methoxy. So instead of being fruits and flavorants molecules, these lead to things that are used in drug treatment, whether it be in proteomics or the para-methoxy is used as a monoamine oxidase inhibitor in the treatment of things like depression and Parkinson's disease. So again, you see the spectra, pretty easy to assign. Sorry, I have the wrong molecule here, but we've got our ethyl group, the methoxy group, and then you get a cis to trans ratio that is actually much more stereoselective than the unsubstituted version. We get about 99.4% trans and 0.6% cis. if I do with the electron donating group, the spectrum is a little bit more messy because I have a little bit of triphenylphosphine oxide still dissolved in my solvent that I was unable to remove, but we get an inversion of what we'd expect. So we actually get 33.3% trans, 68.68% cis. So we're working to improve these reaction conditions and understand and perform the rest of the Gaussian calculations to see if we can understand what governs the cis to trans ratio depending on the pair substituent. So thank you very much for your attention. Thank you to the people at Nanalysis for their conversation, their support, as well as acquiring data. Thank you very much to Len Mueller at Riverside, who's working with us on these Gaussian calculations, Mike Bernstein at Mestrelab for helping introduce me to the SMA, and Enrique for setting this up. Thank you again for your attention, and I'm happy to answer any questions.